Hello, my name is Adrian Stein from the University at Buffalo, and today I'm going to present you my conference paper on the topic Velocity Constraint Time-optimal Control on a Gantry Crane System. This is a gantry crane. Assuming that the velocity of the gantry crane can be controlled, a bang-of-bang control profile is derived to bring the payload from a position of rest to the terminal state with no residual vibrations. Now we're moving the trolley about 10 centimeters. As you can see, there are some oscillations, especially in the first mode. So let me move the trolley for a different position, like so. Now we move the trolley for a different position, and as you can see, the oscillations are reduced. And the first mode is gone. So I ask myself the question, can we derive some closed form expressions why this is happening? Suppose we have an undamped model of a pendulum, like such, where g is the Earth's gravity, beta is the angle of displacement, m is the mass of the pendulum, l is the rope length, and xi is the displacement of the trolley. Therefore, the displacement of the mass can be written like such for a small angle displacement. Here, a spring mass system can function as a surrogate model, where k is the spring stiffness. Let's keep this model aside for now. Let me write down the equations of motion for the spring mass system, which are like such, where v is the input to our system. Normalizing the equation of motion by the mass, m, we can write it in state space as such. And I'm using the following parameterization throughout the presentation. This is our bang-of-bang control profile, where t2 is the mid-maneuver time and 2t2 is the final maneuver time. Furthermore, I'm using the parameterization with t1 as such. So I can calculate the corner points where the switches are turned on and turned off as follows. Let's keep this aside for now. It all boils down to the cost, which totally depends on the final time, tf, meaning how long the maneuver should take, which we are trying to minimize. And this is subject to our system dynamics, which I presented on the earlier slide. We know our initial conditions should be all zero, meaning our position of the trolley should be zero, the velocity of the trolley should be zero, and the position of the payload should be zero. And the final states, which means the final position of the trolley should be xf, the velocity should be zero at the final time, and the payload's position should be xf as well, meaning the pendulum should hang straight down. And we know that our velocity is bounded between 0 and the maximum possible velocity, which I note as vm, for all time. Coming back to our control profile, we can write this in the time domain as follows, where h is a heaviside function. Bringing the velocity from time domain to frequency domain, we get the following equation, where s is equal to bj omega n, and omega n is the natural frequency of the system. To solve for t1 and t2 in this equation, we need a couple constraints, starting with a real and an imaginary constraint as such, and a final value constraint, meaning at the time t2 we want to reach the position xf. Now let me plot, for instance, the switches. Remember, they result from a combination of t1 and t2 when I'm changing the final position xf. This can be seen to my right, where I'm plotting on the horizontal axis the final displacement in millimeters, changing it from 0 to 720 millimeters, and on the vertical axis the switch times in seconds. We could identify 3 different zones. The green area shows that the motor is fully turned on and the trolley is moving at the full velocity of vm. Picking, for instance, a final displacement of 100 millimeters, saying we want to reach with our trolley 100 millimeters and the payload should reach 100 millimeters as well, in a time-optimal manner with 0 residual vibration, we need such a switching profile, consisting of on, off, and on. If I pick, for instance, now 300 millimeters, I'm ending up with a different switching profile, which is on, off, on again. If I pick, for instance, now 500 millimeters, I'm ending up with a completely different switching profile and introduce 2 more switches. So the question becomes as well, what happens at these intermediate stages? Basically saying, what happens in the transition from zone 1 and zone 2? Does it say we don't need any switches at all? I will answer this question later for you. But before we move on, let me play a scenario. Assume I'm giving you as a user a final displacement xf, let's say of 200 millimeters. Can you derive me in a closed form expression what t1 and t2 should be? Or differently saying, can you derive me how the switching profile would look like for such a given displacement? So it all boils down to these 2 equations, where we know Vm, which is the maximum possible velocity of our motor, omega n, the natural frequency of our system, which we know, xf, the final position, and n, which is the number of the zone where we are in. So all I have to do is calculate the times t1 and t2, and this should be fairly simple because I have two equations and two unknowns. However, it turns out that there's a little bit more math involved. So now assume we move with the final position in zone 1, and the equations look as follows, which are pretty simple to solve for. Assume we are moving now to zone 2, we end up with the following polynomial, which is of fourth order. Solving for z will solve for t1, and from t1 we can then calculate t2. Alpha and beta are given values as follows. Moving for instance to zone 3, we end up with a sixth order polynomial, where we solve in the same manner as we solved in zone 2. The remaining question is, can we calculate these collapses in a closed form? The transfer function for this case looks like this, where the mid-maneuver time t2 can be calculated as follows, and from there the final position xf can be calculated. This xf basically marks where these collapses happen. So let me bring the collapse a little bit closer to you. Assume we move in zone 1. The black line is the switching profile, and the blue line is a co-state. From Hamilton's principle, we all know that the co-state is driving the control input, in this case V, as highlighted in the red box. This says when the co-state is negative, that the control has to be fully turned on, and whenever the co-state is positive, the controller is fully turned off. If I'm picking now, for instance, final distances xf as 100, 180, and 240 millimeters, we can see the following evolution of the switching profile. This obviously depends, because of my equation down here, on the co-state. If you focus your view on the peak of the co-state, so the peak of the blue line, you can see that as I'm increasing my final position, meaning 100, 180, and 240, I can see how the peak gets pushed down until it hits tangentially at 240 millimeters the zero line. And this means that my switching profile collapses. Similar observations can be made, for instance, in zone 2. However, now I'm moving at different distances because I'm in zone 2, but as I'm increasing xf, I'm pushing down now two peaks until they hit tangentially the zero line. Because we're in zone 2, we have two more switches than in zone 1, and a pi by omega in phase shift, but apart from this, everything is the same. And a similar observation can be made in zone 3, while if I'm increasing my final displacement, I'm pushing down on the co-state's maximum value until it hits tangentially, or until they hit tangentially, the zero line. And my switching profile collapses. I should tell you that input shaping is placing zeros at specific locations. And for control engineers, these are usually the poles of the system, marked here as a red dashed line, which is illustrating my natural frequency of the system. So as I'm starting the simulation now, you can see that these blue dots evolve over the final displacement, which are marking the zeros which are placed by the input shaped controller at specific locations. And obviously, my natural frequency gets cancelled with those zeros at the specific location. However, from higher frequency spectrum, I can see other zeros evolving. If I'm, for instance, now moving to zone 2, you can see that more of those zeros evolve. And actually, a crossing at the natural frequency is happening as well, at a specific final displacement. I can spin the story a little bit further, for instance in zone 3, and we can see way more zeros evolving now, and the whole picture is getting very messy. However, I can observe again a zero crossing at my natural frequency, and this means I'm placing two zeros at the same location. As a conclusion of this animation, we can say that we place two zeros at a spot which is highlighted in green here, or basically at two spots, one in zone 2 and one in zone 3. And this means I'm creating a robust controller for this specific displacement, even though I did this unintentionally. Now I would like to make you focus on a displacement which is a little bit before the third zone crossing of the zero, and this is at 500 millimeters. Let me zoom in on this picture. And now I would like to make you focus on those zeros which are highlighted here in red. If I plot, for instance, now the residual energy on the horizontal axis, we get the following plot. And I can, for instance, illustrate now, if I'm increasing the maneuver, in which direction those zeros would move. which is highlighted by the arrows here. You can see that this and this zero are going to collapse as we've seen previously in the animation. Plotting, for instance, now the residual energy of a robust controller on top of this, we can see the following. At a specific final displacement, these two zeros are getting overlapped and the non-robust controller is going to be equal to a robust controller. We can say as well that for higher frequencies, where we have, for instance, unmodeled dynamics, a non-robust controller might do actually better than a robust controller, because you can see that the residual energy at this higher frequency, for instance, for a non-robust controller, is lower than for a robust controller. Now let me show you our experimental setup before I show you some videos. This is our gantry crane, driven by two NEMA 23 stepper motors in this direction and one NEMA 23 stepper motor in this direction. I'm just looking for displacement in this direction for this presentation. The drivers of the stepper motor are set to 400 steps per revolution, meaning that the trolley can move at 240 millimeters per second at max. Zooming in at the payload results in the following picture. This part is a chassis and is 3D printed. Inside the chassis is a 500 gram steel mass. And if I cut this open, for instance, now as shown here, you can see that inside there's an Arduino Nano which gets data from a gyroscope and is then connected to a transmitter which sends the data to another Arduino Nano which has a receiver. The power bank is powering that module. We are just interested in the rotation around the y-axis, which I call alpha. For those of you who are unfamiliar with modes of a system, I'm going to show you the first and the second eigenmode. Here you can see the first eigenmode, and this is a second eigenmode. Before I show you the video, I would like to tell you that we're displacing our trolley for 10 centimeters and our rope length is 45.5 centimeters for now. Then I can decide if I want to cancel with my controller one mode or both modes. And for both controllers respectively, I'm having a non-robust and a robust solution. You will see later what I'm going to mean by those non-robust and robust and 1 and 2 modes by showing you the videos. So let's start with our one mode controller and the non-robust version of that. I'm moving my trolley for 10 centimeters, and as you can see, right after the maneuver, I'm having a second mode oscillation, meaning I canceled my first mode, however my second mode is still remaining, as you could see in the previous video, remember? And this can be seen here as well in the zoom picture. Now let's go ahead and apply, instead of the one mode non-robust controller, a two mode non-robust controller. How would this look like? You can see that right after the maneuver, both modes are cancelled. However, there's a little bit of remaining oscillation after the maneuver. And we would like to get rid of that. So instead of doing a non-robust version, let me do a robust version of this. And this looks as follows. Right after the maneuver, you can see that the oscillations are almost completely gone. And to be precise, compared to the previous video, we reduced this oscillation by 69% in terms of residual energy. So should we go ahead and, for instance, induce some uncertainties in the system by, for instance, changing the rope length? Therefore, I designed this apparatus which allows us to change the rope length in 15 stages. So the rope which holds the payload can be placed in 15 different stages by a stick, as you can see here. And the rope can be made longer or can be made shorter. However, I'm deciding to make the rope shorter. From a front view, this looks as follows. We are just lifting up the payload by almost 6 centimeters. However, the controller doesn't know about this change. So now we can see how a non-robust and a robust controller perform compared to each other. So I'm going to start with a two-mode non-robust controller. And the video looks as follows. You can see that right after the maneuver, we have a lot of first mode oscillations and a little bit of second mode oscillations. And this is because we changed the rope length and the controller doesn't know about it. However, if I'm applying, for instance, now a robust version of this, we can see the following video. Right after the maneuver, you can see that the robust controller took way more care of this uncertainty. And this is the advantage compared to a non-robust controller. However, in nature, nothing comes for free. And even though you don't see it, but the robust version takes a little bit more time than the non-robust version. However, it accounts greatly for the uncertainty by keeping the oscillations as small as possible. So I made actually the effort and conducted 150 experiments for all different 15 rope length stages which you could see previously. Not just too short, not just too long or in the middle. No, for all 15 different stages. And each bar, which you can see red or blue, is summarizing 5 experiments. And to make the figure a little bit more grasping for you, I plotted again the observations which we made from the swinging velocity in those 2 plots and in those 2 plots, where this is the unchanged rope length and this is a changed rope length. As we expect for a non-robust controller, the shape of the residual energy looks very sharp, like almost like a wedge. However, the robust residual energy is staying flat when plotted in the same scale as the non-robust version. This research revealed several features of a time-optimal controller when the velocity is constrained. We were able to write out closed-form expressions for the birthing and the collapse of the switches, and we could identify different zones. Robustness studies were performed theoretically and experimentally on a self-built gantry crane system. And uncertainty studies were performed by changing the rope length of the pendulum, and it could be seen that the robust controller is outperforming the non-robust version. From the loci of zeros, we could see that the non-robust solution is sometimes coinciding with a robust solution, meaning that the developer of a robust controller doesn't have to put extra effort into the optimization process. We would like to thank the National Science Foundation for the support of our work, and if you have further questions, please feel free to contact us. Thank you.